Okay, I think most of us are here. Good morning. It's day 5 of the CSM tutorial. It's finally day 5 of the CSM tutorial. I know the days were long, maybe because we kept waking up at ungodly hours. So today's daily brief would be very brief. I'm just going to go through the agenda of today. This morning, we're going to have 2 special talks. The first one is about simpler models by Brian Menderos, and the second one is variable resolution by Adam Harrington. And then we're going to go into one break with coffee and snack together. And then after the break, we'll have a talk by Steve Yeager on Earth system prediction. So all of this morning's talks are the special talks, which are 30 minutes long. So they are one of those short talks. And then we will have intro to lab, because today we'll have the breakout challenge exercises. We will have multiple scientists coming in to give an intro for each of these breakout lab. And then from 10:30 on, we can go into the morning lab exercises. And then lunch, we won't have a meta scientist today, but we will still have the Mesa Lab public tour if you still want to do one. And then in the afternoon, Jim Edwards will give a talk on model porting. This is about how to port CSM model to your own HPC in your own institution. I believe this talk will be a virtual talk. And then the last talk of the day would be from Monica Morrison about how CSM can be used for actionable science, linking it to the real world. So the afternoon will be lab exercises again on the breakout challenges. And then at 4 p.m., a little bit earlier today, we'll have the final wrap up. It's a bit of a long wrap up. And then the shuttle also leaves early today at 4:30. So for the lab today, as we talked about, these will be the challenge exercises. I think many of you may have already started looking at this yesterday or by accident, because we kind of arranged it in a different order. We should have put diagnostics in front of challenge exercises. It's kind of caused a little bit of, oh, my coffee, little bit of a confusion. But today is the challenge exercises. You can find, again, your favorite section to begin with. And if you have time, you can explore other topics as well. And I think that's all I want to say about today's activities. And Elizabeth and I, we noticed yesterday there was almost no survey results coming in. So we wondered maybe it's because we didn't leave enough time for you to complete the survey yesterday. So because we will have the daily survey for today and the full survey also for today, on top of yesterday's will be too much. So we hope you can fill out yesterday's survey if you haven't already, throughout the day when you have like 5 minutes or so. Okay, sounds great. Question?
Oh, I didn't either.
It was in the Slack, I think.
Yeah, in Slack. Oh, okay. Yeah, we can resend that in email. Maybe Slack. Yeah, Slack maybe a little. Okay. Thanks for letting me know. Okay, other questions?
Great. Okay, great. So let's now have welcome Brian Menderos for our first talk of the day on simpler models.
Okay. All right, I'm Brian Medeiros. I'm a project scientist here in the climate analysis section, and my research is mostly about clouds and cloud feedbacks, which you probably have heard about a little bit this week. It's a complex topic, and so one of my favorite ways to think about how to study the way that clouds interact with the climate system is by simplifying the system and looking at simpler versions of the model, which is what I'm going to talk about today. Pointer, let's see if I can use this. Oh, that's terrible. Okay, I'm not going to use that. I know from looking through the slides from earlier in the week that you've been introduced to some of the complexity of CESM, microphysics and land surface models and ice and everything. And I'm here to tell you that there's still room for spherical cows. We can do things simpler and try to understand. So this is a talk that usually Isla Simpson gives. So she gave me a whole bunch of the content for the slides, but then I put my own version of it together. So we know that understanding model solutions or system models are complex. It's hard to like dig in and get to really deep understanding, and that's because everything's connected together. Everything's changing all at once. This picture on the right is actually showing an analysis of the code base of an earlier version of CESM. And so the size of the bubbles are basically the lines of code, but this is representative of the complexity of the system too. So each of the systems that we're coupling together is complex in its own, and then they're also strongly coupled and interacting with each other, as shown by the little arrows going through the coupler in the middle. And so that strong coupling and interacting is how the model kind of establishes its own equilibrium or quasi-equilibrium, and that's through its constraints, through conservation of energy and momentum and mass and water and things like that. But the problem is understanding how you get to that equilibrium is hard because everything is always changing. So and we know that also the system is so complex that it takes a large computer, a lot of computation to even get to the solution, and it often will take a long time on those big computers. So we're going to start to think about how we can start to pull it apart and understand it. And so there's lots of methods to do this. Broadly, you can think about just doing a really detailed analysis of the model output, which is what we all do all the time. It's an important component of it, but it can be difficult, and you can get to the point where it's ambiguous about what is the solution, what's the answer. So you might want to do then perform some kind of idealized experiment or some kind of experimentation with the full comprehensive model to try to isolate something that you're looking at, and that's a good way to go about it as well. But you still might have some ambiguity or some complexity that you can't come and disentangle. And so another approach is to simplify the system itself and do experiments where you can understand the system without doing quite as much work. And so that's what I'm going to be talking about today. We have a number of idealized configurations within CESM. It makes it relatively easy to run a lot of different kinds of models, and the capacity to do that is growing all the time. And we have a Simpler Models website that I'll point to a few times during the talk that you can go and read more details about. So what I'm going to do today is kind of take you through a series of configurations that we have, just show you some examples and give you a flavor for what we can do with CESM almost out of the box. Mostly out of the box. So I know Dave Lawrence showed this picture on the first day of the tutorial, kind of showing how we have these different pools when we're doing climate modeling. We want higher resolution, we want more complexity, we want a lot of ensemble members. I'm going to be talking about the complexity part of it today and trying to reduce that complexity mostly for understanding. And so this is my version of this little star that he had coincidentally in his talk. This is from a perspective piece that came out just this week in AGU Advances, if you want to check it out. You can think about the hierarchy of Earth system modeling in this way, where there's all these interacting different kind of configurations, and you can go from one to another by changing different aspects of the system. At the top is like the perfect model. It's like the digital Earth, the most sophisticated model you can imagine. And then if you go kind of counterclockwise around the illustration, you get to Earth system models that have parameterized processes or simplified versions of the processes, but might still be very complex. You might start to idealize those processes more to get to more simple versions of Earth system models. And then if you keep idealizing processes, you get down to kind of analytical or very simple models, barotropic models or energy balance models or something that's really conceptual, that really is the basis for our understanding of the system. If you instead you go the other way, the clockwise around the illustration, this is simplifying the forcing or the boundary conditions of the system. So you might decouple the system and only look at one component. In this case, it's the atmospheric component. And you might keep going and take away the land and the topography and make an aquaplanet. We'll talk more about that in a few minutes. And if you keep going and idealizing the boundary conditions and the forcing, again, you kind of get back to these conceptual models that underpin our basic understanding of the system. So there's a lot of reasons you'd want to do that, and I kind of just laid that out. For understanding things, reducing the complexity allows our brains to actually comprehend what's happening in the model. The other things that are good about simpler versions of Earth system models are that they are often easy to perturb. They allow for idealized experiments that allow those causal pathways to be isolated and understood. They're usually much cheaper than running the comprehensive version of the model. And they allow for parameter sweeps, so you can do a lot of experiments, and a lot of that is because of these other aspects of the model. They're cheaper to run. You don't have to run them as long, so you can do a lot of runs with them. What are the cons of doing simpler configurations of models? The only one that Isla and I can come up with is that they are less realistic. They are more challenging to compare with the real world. That's not to say you can't. We can do that. You just have to be a little bit more creative about how you do that comparison and a little bit more aware of what are the assumptions going into it. So I'm going to start with the atmospheric component. This is where we have the most configurations available to us in CESM. This is an illustration that shows all the configurations that we have. Going basically in the vertical is basically that forcing complexity that we talked about before, or boundary conditions. And then on the horizontal is basically physics complexity. This is very rough, don't take it too literally. But down at the lower left will be like these fundamental models, conceptual models. These are not in CESM. You have to do these on your own, either with pencil and paper or with some idealized numerical approach. But then we get into what we do have in CESM, dry dynamical core configurations, dynamical core configurations that have idealized moisture, gray radiation aquaplanet, radiative convective equilibrium, aquaplanet, and the full-on atmosphere model, CAM. And I put in nudging and cloud locking inside of CAM. These are two configurations where we constrain the simulation to be closer to some pre-specified state. Nudging, it might be the dynamics, and cloud locking is the cloud cover. Nudging is supported in the model, and you can run it. Cloud locking is not officially supported, but it's pretty easy to set up, and we have instructions for how to do that. These other configurations are all available in the model, and the model versions where they became available are highlighted in the legend. We also have the single column atmospheric model, SCAM or SCAM, and I put down here because it's much simpler in terms of its forcing complexity, but it does have the full atmospheric physics, and I'll show you an example of that in a bit. So I'm going to step through these configurations and show you some examples, just try to give you a better explanation, understanding of what they are, starting with the dynamical core. And we have a couple of different versions of dynamical core configurations. This one is the Held and Suarez configuration. It's based on this paper by Isaac Held and Max Suarez from 1994, which is linked here. And basically what you do is you take the dynamical core, the equations of motion, and on the right-hand side of the equations, the forcing side, you get rid of everything except for basically a linear drag for the momentum equation and a simple relaxation for the temperature equation. There's no moisture and there's no radiation in this configuration. The lower boundary is just a flat surface with some surface drag. There's no topography, there's no ocean, there's no land, there's just a surface. This currently runs with all of our dynamical cores, so you can compare them pretty easily in this one configuration. It's super cheap to run, and the comp set is FHS94. So you've been running these configurations in the exercises where you just do create new case, case setup, case build, case run, or submit. You do the same thing with it. You just change comp set in your create new case to this, and you get it out of the box. The simulations look kind of Earth-like when you look at them in terms of zonal mean circulation. You get the western jets, you get eddy momentum transport. This configuration is good for any kind of dynamical exercise where you want to look at the dynamical interactions like eddy-mediated or eddy mean flow interactions or things like that. And it's super easy to perturb because you only have these couple of parameters in the model itself. If you need to go even simpler and you really want to dive into the dynamics, the representation of the dynamics in the model, we also have a comp set called FADIAB, or ADIAB. This is what's used in DCMIP, the Dynamical Core Intercomparison project. There's no forcing at all, it's just the dry dynamics. This is used for baroclinic wave test cases and things like that, which maybe Peter mentioned in his lecture. If you want to go to a little bit more complex configuration, you can add an idealized moisture to the Held and Suarez configuration. That's what's shown here. This is the FTJ16 for Thatcher and Jablanowski, 2016. This adds a very simple representation of moisture to the model. Basically what you do is you have a tendency equation for water vapor that looks like this. This is just a representation of condensation. So if the grid cell reaches saturation, you condense, you immediately rain out whatever condenses, and it goes away. So there's no clouds in the model, but you do have the diabatic forcing that's associated with that phase change. And so this gives you a sense, and you're running this on a water-covered surface, so you get some sense of precipitation climatologies that look like this. So you have an intertropical convergence zone, you have storm tracks that are raining, and this is gives you a sense of the zonal mean circulation in temperature in the colors, which are basically still this Newtonian cooling from the Heldon-Suarez configuration, plus the diabatic heating from condensation. And this is the zonal mean zonal wind in the contours. This is a time series of the precipitation near the equator. You can see there's some propagation. And this is a snapshot of the circulation at one arbitrary instant. We'll see a comparison showing where we expand this figure into a few configurations as we go along. This kind of idealized moisture configuration is good for dynamical studies that do involve some kind of interaction between moisture and the large-scale flow, basically that diabatic heating, but without clouds, without the radiative feedbacks associated with them. Now we can add some of those radiative feedbacks back in by going to the next configuration, which is the gray radiation aquaplanet. This is a configuration that was really developed by Dargan Frierson about almost 20 years ago now in a series of papers using the GFDL AM2 model. And sometimes that's called grams if you see it in the literature. And what we've done is implemented that entire model into CESM as this F-gray-rad comp set. What it does is it has a slab ocean, which is different from the other configurations we've been talking about. So it has a consistent surface energy balance. It does have a representation of radiative cooling. So it's gray radiation. So the cooling is really just like sigma t to the fourth, basically, where the sigma t to the fourth is being controlled by the emissivity of a specified long wave absorber. The radiation doesn't see the water vapor. So you have water vapor that's very similar to what was in the moist Held-Suarez configuration, where you have condensation and diabatic heating, but the radiation doesn't directly interact with it. It only interacts with the temperature. There is surface or shortwave radiation, but it only gets to the surface. The atmosphere is completely transparent to the shortwave, so it's just for the surface heating. There are no clouds again. There's bulk formulae for the surface fluxes. And despite making it seem like this is a super simple, highly idealized configuration, when you run it and you look at like the zonal mean circulation, looks pretty Earth-like. When you look at the precipitation, it's pretty complex. There's a lot of structure in it. And when you look at the circulation snapshot, you can see that there are these large kind of storms, like very Earth-like configurations, given the simplification of the lower boundary condition. So it's good for a lot of things, but if you're interested in the interactions between moisture, radiation, and circulation, that's the sweet spot for this one. The next configuration we have is radiative convective equilibrium, and this is where we take a big step up in complexity. So we're leaving behind the idealized physics and going to the full atmospheric physics from CAM. What we're doing now is going basically through the other path of that figure that I showed you at the beginning. Now we're going to simplify the boundary conditions and the forcing. So what this does is we turn off the planetary rotation, we make the surface boundary condition homogeneous, we make the insulation homogeneous. So you can think of it as taking the sun and stretching it around the planet and making it constant. So there's no diurnal cycle, there's no seasons, and there's just a constant sunshine everywhere all at once. So you have this very homogeneous system where basically the only thing that can happen is that the atmosphere can convect and the atmosphere can cool. And you reach this radiative convective equilibrium. The configuration we have implemented in CESM follows the RC-EMIP protocol by Allison Wing. And you can run it with prescribed SSTs or slab ocean. And these are some examples of what the precipitation and outgoing long wave look like from a paper by Kevin Reed. This is really useful for looking at convective organization because that's basically all you get. The convective dynamics sort of do what they need to do to balance the long wave cooling of the system. So you get this kind of self-aggregation of convection forming and feedbacks between convection and the regional circulation. It's also really useful for comparison with cloud resolving models or large eddy simulations, which are also usually run with these idealized domains, but at much higher resolution with more sophisticated physics. The next step up is making the boundary conditions more complex. This is the standard aquaplanet configuration. This is my favorite one. This one is basically you take CAM, you take away the continents, you take away the real SST and prescribe like a really simple SST that's warm on the equator, cold at the pole. You take away the seasons, you take away the sea ice. You have this zonally symmetric configuration of the full atmosphere model. Over a simple, so it's a simple water-covered Earth. You can have a slab ocean if you want, or you can specify some other SST distribution if you want. And this is good for a lot of things, actually. It's been used for almost everything you can imagine in atmospheric science. One of the reasons it's so good for so many things is because it has the complexity of the full atmosphere model, but you get a much higher signal-to-noise ratio because the zonal symmetry and the hemispheric symmetry that you get allows you to run really, really short runs and get really good sampling. So even though it costs about the same per time step as the full atmosphere model, you only have to run it for a few months to get good results, good statistics. And so now we can see this figure has been filled out where we can compare the moist-held Suarez, the gray radiation, and the aquaplanet all together. You can see that they have a lot of similarities, but their differences emerge, like the characteristics of the tropical precipitation are totally different. And you can see these kind of Kelvin waves emerging in the full aquaplanet, for example. If you wanted to go in a different direction, we have the single column model. So that takes away the dynamics altogether. And now we just have the full atmospheric physics in a column. This is a super cheap configuration to run because you're literally doing no dynamics and just solving the physics in one column of the model. So you can run this on a laptop in a few minutes. And you get a time series of everything that you'd get from the physics. You prescribe the lateral boundary conditions for the large-scale circulation and basically the location of the column to give you the forcing from the sunshine and the SST. This can be set up as FSCAM or FSCAM. And we have a number of standard cases to run with the single column model, or you can build your own case. This is really good for parameter sensitivity studies, or if you're developing a parameterization or a part of a parameterization, this is exactly where you should start because it's so cheap and so fast to iterate on. All right, a couple of minutes on going to more complicated coupled configurations. And so you might be thinking, well, that's a lot of stuff about the atmosphere, but I only care about the land or the ocean or the ice. So you can do simplified configurations of those with those components in some ways. We don't have as much capability there, but we're building it. So if you're thinking about trying to do something with idealized land for climate dynamics, like having an idealized continent, you can hack the aquaplanet. This has been done in experiments like TrackMIP, where they put in this a continent that's just a big tropical continent into their aquaplanet configuration. They represent it by putting a slab ocean in that section, right? But then changing the characteristics of the slab ocean to kind of mimic land. So you can change the albedo and the evaporation and the roughness of that patch and get an interactive surface, which is useful, but it becomes fiddly at some point when you start to do a lot of things. And so you might want an actual land surface. So CLM, as you've seen, is really complicated. So we do have the capability to run this thing called SLIM, the Simple Land Interface Model, developed by Marisa Legou. It's a really simple, it kind of like goes back to the old days of land surface modeling where it's just a few layers of soil, some specified albedos and roughness, and a bucket hydrology model. So that's a really simple configuration. You don't have to worry about plant functional types or anything. It's perfect for if you need an idealized continental configuration or maybe a paleoclimate or exoplanet kind of configuration. This might be something that you'd want to look into. It is almost implemented in CESM. It works, but it takes a little bit of extra effort to run it. So if you do want to experiment with SLIM, let Isla or I know, and we can get you in touch with people. Eventually, we are hoping to get this into CESM 3 as a standard configuration. If you want to start to look at the ocean or the coupled atmosphere ocean system in idealized configurations, we're building out those capabilities as well. This is building basically on the work by Xiaoning Wu and colleagues that coupled MOM6 to a CAM4 actually, and ran the aquaplanet and a simple ridge configuration of the ocean. The ridge is basically like you have just a strip of land from pole to pole. Isla and others have a project where they're trying to make this kind of configuration easier to run, where you can define bathymetry and continental geometry and land surface properties in a simpler way. And one of the things that has come out of this project is this tool called Visual Case Gen. It's a graphical user interface that walks you through all the steps necessary to configure the model and configure the boundary conditions that are needed to run the model in these kind of idealized configurations. So if you needed to change the continental configuration and couple to MOM6 to CAM5, this is a good way to try to start building that configuration. And I think that it's released in the development version of CESM, so you can check it out and start playing with it. And there's a website that gives you instructions for how to do that. And here's an example over here that just shows an idealized continent being built up and with a little mountain range, and then eventually adding like land biogeochemistry and things to it, all coupled to MOM6. The other ocean configuration I wanted to mention is an emerging configuration that's not quite available yet, but it is running in some versions of CESM. It's called the pencil model, and it's somewhere between the slab ocean configuration and the full dynamic ocean, where every grid point of the ocean model is represented by a column, so it's like a single column ocean model everywhere. And so you get the vertical physics of the ocean coupled to the atmosphere, but you don't have the horizontal transport in the ocean that's specified. So that's Young-Oh Kwan and Yvonne Lima and people at MIT and Woods Hole and Gokhan Dunn and Basaglou here developing that configuration. If that's something you'd be interested in, you should probably get in touch with them. I know that they have long configurations running, but it's not something that you can run out of the box with CESM yet. So wrapping up, I think simpler models are super interesting, really useful for getting at process understanding, also for doing development of the model. A lot of them are much cheaper to run than the comprehensive version of the model. Some of them even run on a laptop. We have good documentation of our configurations on our Simple Models website, which is linked to here again. We also have a section of the CESM Discuss bulletin board which is devoted to simpler model configurations, where you can get in touch with us if you have questions. I also put Isla's and my email here if you want to get in touch with us directly. That's it. Thanks. Yes, so a number of the single column configurations are over land points, and I think that they do, by default, couple to some version of CLM. And so you should be able to do that coupling in a single column without a problem. That's also true for sea ice, I believe. So you can run the SCAM over sea ice point and have the sea ice model running, I think. I've never done it myself, so I can't promise that it works, but I think it's supposed to work.
With the single column model, what forces the physics? So like if you wanted to look at convective parameterization, how would the convective parameterization get kicked off without the dynamics?
Yeah, so what you do is you basically you use boundary conditions, so you give it something, some kind of circulation forcing. Usually it's just the wind components, the horizontal wind components, along with the surface temperature, maybe a little bit of like moisture and things. There's not too much. You can also, there's a few other permutations of the forcing that you can apply, like if you wanted to specify the surface flux instead of the surface temperature, I think you can do that. But you have to give it something on the edges to give it that large scale population to interact with. And that will kick off the convection.
Okay, thank you.
Does this visual gen tool work with POP configurations or only MOM6?
I believe it only works with MOM6. But that's the future.
Question?
I have one technical question that if we, when, based on your experience, if you want to incorporate more process or make it the model more complex, or you try to reduce or to off some process, make the model simple, which one you think is difficult to deal with, like some coding or something?
Oh, from like a coding perspective, it can go either way, honestly. Sometimes it's very easy to make things simpler, but that can break the model. Like you can literally get to the point where you're just literally commenting out lines, and so you don't have to write any code to make the model simpler. But you can also get into a case like the cloud blocking configuration that I mentioned earlier is simpler in the sense that the clouds are prescribed, but it requires quite a bit of code modification to get that to work. Going complex is harder because you have to write code that's representing some complex system and then coupling it to this already complex system. So I'd say in general, that's the more difficult challenge. But it's more difficult because it's also, you have to understand the more complex system and how it interacts with the even more complex system.
I'm also interested in the SLIM model. How does that couple with atmosphere? Is this only for land itself? Or?
It's for land itself, but the way it's been designed is, and the way I'm hoping that it will be finally implemented in CESM is it will be a drop-in replacement for CLM. So it will couple to the atmosphere in the same way that CLM does, but with a much simpler representation that gives you the fluxes from the land to the atmosphere.
Oh, it can be another option.
Yeah, so I'm hoping that that in the near future, you'll be able to do an experiment with CLM and then simplify it down to SLIM to see and the difference will show you how the complexity of land surface affects the simulation.
I remember Marisa also had a paper about stripe or cap, different continent moving around. Is this in
No, that would require some extra effort, but visual case gen might be able to help with that kind of configuration if it could couple to SLIM, which hopefully it will someday.
Can you explain a little bit more about the cloud blocking experiments? Do you prescribe, for example, the cloud macro properties or prescribe, for example, the cloud radiative properties? Like radiative effect?
Yeah, so from a big picture perspective, cloud blocking is a lot like nudging in the sense that we put clouds in and are constant, and the radiation scheme only sees the clouds that we specify. Kind of like when you specify the circulation, it's relaxing toward that circulation, so you constrain the model. In a more detailed way, what we do is we take the cloud properties and we intercept them right before the radiation call, and we replace them with what we want. And that's a couple of microphysical properties as well as the cloud water paths, ice path, and cloud fraction. And then the radiation sees that, and then we go back to the predicted version of clouds for the rest of the calculation.
So you didn't cut off the interaction between clouds and the radiation?
We make it non-interactive with the circulation. So the radiation sees the clouds, but they're not the clouds that the circulation sees.
Thanks.
With the simpler atmosphere models and kind of, I guess, sort of going off that, like, are aerosols in any of them or like prescribed, or like how does the radiation and or like, I mean, I guess if clouds are prescribed, they wouldn't necessarily see aerosols, but wondering how that would incorporate.
I'm gonna skip the cloud locking part because that might be complicated and I don't think I'll answer that correctly. But the rest of our configurations, if we go back to, so there's no aerosols in the super simple ones, the dry dynamics, idealized moisture and gray radiation. There's no aerosol at all. The gray radiation, you could probably like alter the parameterization of the optical depth to mimic something like an aerosol. In RCE, Aquaplanet, and CAM, they all have the capability of running the aerosol scheme that CAM runs. By default for RCE World and Aquaplanet, we turn it off and we use a specified drop number and ice number concentration. But I have a paper, for example, with the Aquaplanet where I go back and I mess around with aerosol emissions and run the aerosol model. It's really easy to do. It's just nameless parameters, actually.
Okay, for the sake of time, we couldn't take more questions. You can catch Brian in the break. Okay.
Thanks.
Our next talk is on variable resolution, and you'll hear it from Adam Harrington.
You're gonna need this.
Okay. Ceiling mics. Thanks. Oh, is there a slideshow? Yeah, there you go. The second to the last slideshow. Awesome. You like it? Formatting, or at least the formatting's locked. This needs to go here. Hello, hello, hello. I'm gonna pre-stage these YouTube links because I don't know if they're gonna work. There's always ads in YouTube. Oh, not for you guys. Okay, great. All right. Yeah, I'm Adam Harrington, project scientist here. I'm going to talk about variable resolution CESM. So we'll start off with the basics of what is it, why use it, and how to use it. So variable resolution is CSM's label for what we call static mesh refinement in CAM. And static mesh refinement is just one type of a grid refinement approach, and it's the approach where you have a global model that you're refining your mesh in a region of interest, and that refinement, for example, might be over the Arctic or the North Atlantic, and that mesh is sort of statically refined. It's not changing in time. The nice part is it's just one model, whereas you have another type of grid refinement called domain nesting, and that's a little clunkier. That's like when you have a limited area model that's high resolution embedded into a parent global model. And that global model is sort of providing lateral boundary conditions for your limited area model. And there may be one-way or only two-way interactions with the parent model. And so NWS uses a domain nesting model actually to forecast our hurricanes. But it is two different models, and so these models have different assumptions, different physics parameterizations, and so you have to accept these inconsistencies between these two models. And so static mesh refinement's a little bit nicer in that you just have one global model, and that's what we use in CAM, as I said. There's a sort of holy grail of mesh refinement called adaptive mesh refinement, and that's where it's one global model, and the grid sort of evolves in time depending on where you want resolution. So for example, if a front is forming or a tropical cyclone is starting to form, you might want to throw more horizontal resolution at those features to better resolve those processes. And so the mesh is actually dynamic in time, which sounds great. There's not any operational atmospheric models that use this. They're all sort of research tools at this phase. And so it hasn't really been matured that much in the atmosphere. There is an example of an operational ice sheet model. It's called Bicycles, and it's from the Department of Energy, and it's that's the YouTube thing I opened up. And so this YouTube video is going to show you a visualization of the grid resolution and the colors in a retreat scenario of Antarctica. And so you want to actually add a lot more resolution at what's called the grounding line. That's where the ice sheet meets the ocean. It's not where the ice sheet calves, but it's actually where the ice sheet thins so much that it can actually float. And you need to have more resolution because your stress balance changes a lot in that region. Let's see if we can show the other one. Of course. Are we going to wait the 3 seconds? Yeah. Okay, so this is just showing a more dynamic field. So you have this retreat of the West Antarctica and showing the ice velocities in the front of the glacier. So anyways, that's an example of adaptive measure refinement that's quite powerful, actually. So why do we use variable resolution? Well, the appeal is because you can simulate high resolution in a global model, but at an affordable cost. So it's, in some cases, impractical to run a global model with very high resolution everywhere for very long time periods. And so in order to deal with these computational bottlenecks, refining only in a region of interest can save you computationally a lot. And so this is just an example of the wall clock time from a run using a uniform, I believe, quarter-degree mesh, and then the refined mesh here, which just, I think, refined somewhere in the North Atlantic, and it's about 5 times cheaper. So that's kind of the number you end up getting from regional refinement as compared to the globally uniform high-resolution version is on the order of 5, 10x speed up, so it can really help you get more out of a lower allocation of core hours. So we have 2 dynamical cores in CAM that support variable resolution. The more recent one is the MPAS-A dynamical core, which was developed down the hill at M cubed. We have recently ported it into CSM, so now CSM users can run it. That wasn't always the case. The grid is called, it's a bit of a mouthful, but it's called spherical centroidal Voronoi tessellations. They're just hexagons. There's a couple pentagons, but for the most part, everything just looks like a honeycomb. And when you make a refined grid, you have like a density gradient that you create, and it gradually refines into the region of interest. It's a fully compressible non-hydrostatic model, meaning that if you want to run at resolving scales that are 10 kilometers and less, you need to have non-hydrostatic dynamics. And so for very high resolution regional refinement, MPAS would be the way to go. The spectral element dynamical core has been in our model for a bit longer. It was jointly developed between NCAR and DOE. But about 20 years ago or 15 years ago, we kind of had a divorce with DOE. And so we had a hydrostatic version that's been in CSM2 for a while. That's going to be our workhorse model in CSM3, which we should be released in the next year. And the DOE folks, as they kind of forked off with their version, started to adapt it to be non-hydrostatic. And so we now have a new project called Storm Speed that's bringing the non-hydrostatic version from DOE back into CSM. And so that's going to be usable for people in the near future. It's a cube sphere mesh, and so I think Peter probably went over this on Monday on the DICOR talk, but basically it's a 6-sided cube, like a dice, and you kind of blow it up to like a balloon to be like a sphere. And so you have this, and then each one of these 6 faces is sort of divided up into these quadrilateral elements. And then each side, each element, you have a finite element solution. So you have actually structure of the solution inside each element. We actually have 3 VR grids that run out of the box in CSM3, or CSM right now. When we release CSM3, we're going to have 5. And so right now, you guys can check out the code and run variable resolution right now for 3 of the grids. And there's a link here if you want to reference later on how to do that. So in order to sort of understand what is it that you have to sort of modify in the model in order to support regional refinement, effectively all the things that you would modify when you increase the horizontal resolution of the model. So number 1 is that the numerical filters in the DICOR, basically you need to scale them back so you have less sort of diffusion, and so you can support smaller scale features. And so we have a scale-aware tensor hyperviscosity that adjusts the diffusion depending on the local grid cell and as it changes in space. You need to reduce your time steps, both in the dynamical core for stability and in the physics time step, not necessarily for stability, but just for accuracy. And you need to increase the resolution of your boundary conditions. So in order to prepare like a topography data set to be run in a particular model grid, the first thing you have to do is you have to filter that topography so it doesn't have any 2 delta x scales in it, where delta x is the resolution of the model grid that you're running with. So in a 1-degree model, 2dx is like 200 kilometers. So you're sort of filtering out all these 200-kilometer scales, and that is you preparing it for this 1-degree model. And the reason is because 1dx and 2dx modes are actually not accurate in the dynamical core. We have filters that remove them. That's what number 1 does. And so at higher resolution, you don't need to smooth your topography as much. And so you can support, obviously, rougher features, which is indicated here by a progressive increase in resolution of the Himalayas, going from 1 degree, quarter degree, down to, I think this is 14 kilometers. You also want to resolve, you can resolve sort of more complex, coastlines and ice sheet margins and even small mountain glaciers, so you need to adjust your surface data set properties. Okay, so part 2 is about regridding. Regridding is important not just for folks running variable resolution, but in general, regridding is something that people who analyze model output do all the time. We have to regrid our model output to the observation data set grid so we can compare to observations. So it's an important tool. But to get to the point of why you need this more for variable resolution is because most variable resolution models work with unstructured grids. So we're all familiar with structured grids. If you've been in atmospheric dynamics, we derive the equations of motions on a latitude-longitude grid. It's two dimensions, and they're structured in that you increase the latitude index and you go further north. You increase the longitude index and you go further east. And so you know where you are on the grid. It's a graph. And so they're structured to the coordinate. And that makes it easy to do zonal means, where you just average over the longitude dimension, or stream functions, where you have to take gradients in the latitude and the longitude direction. Unstructured grid, the horizontal dimension is flat, it's just 1 dimension, and there's no structure to it. So if I have some index I that pertains to this grid column here in the side of the United States, the next grid column I plus 1, it may not be next to me, it may be on the other side of the Earth. There's really no need for there's no structural information in the indices. And so you don't have a latitude and longitude. And so if you have to compute a zonal mean, it's either extremely difficult and non-trivial, or you just regrid it to a lat-long grid, and that way you can do things like zonal means and stream functions. So how many people have regridded model output before? How many people here think they've got it down, they can reproduce it, they have a great workflow? Come on, I know you got your hand. Yes, special weights. Right, an expert would know how to generate weight files for an arbitrary grid. And I think it's a tool that's worth learning. There are some instructions here. I'm not going to go through them now. Because last time I did this, I got feedback saying that this is boring. But I do have the information here for, how do you, if you have the weight file, how do you regrid? There's options for how you do it. And how do you generate a weight file? And so both of these steps are important, and I think you can reference these slides if you wanted to do that in general. So we're going to move on to part 3, the applications. I'm just going to give you a couple examples of variable resolution science studies we've done. There are so many more, and I don't have all the time to go over them. But I'll start with this study we did on the response of storms to SST anomalies in the North Atlantic. So this is a 1 degree grid on the bottom here. This is a 1/4 degree refined over the North Atlantic in the middle. And here's an 1/8 degree refined over the North Atlantic at the top. And we added an SST anomaly to this dotted box here, and we watched storms pass over it. So in the 1 degree model, storms are sort of represented as a single entity. So the colors are the precipitation rates, and this little contour here is the updraft, the resolved updraft from the dicore, or I should say upward motion from the dicore. And so it's just one continuous feature. Your front is represented as one continuous feature. That's all you can really support in a 1 degree model. If you go to a 1/4 degree, the model grid can start supporting sort of individual convective elements that can populate the front of your storm. And so these yellow lines are updrafts, and the purple is downdrafts. But then you go to 1/8 degree, and now you can really fit a bunch of these convective elements to start pixelating a more realistic depiction of what a front looks like. And so it turns out that the sea level pressure response as a function of resolution is very different. And it isn't really until you get to this 1/8 degree situation where you actually result with something that resembles an NAO type pattern, and it's statistically significant. And so, in short, these 1/8 degree models can support these convective elements that end up transporting heat and momentum upward and poleward. Whereas there's not nearly as much vertical mixing in these lower resolution grids to transport the momentum and the heat. And so you get a different response, and your interannual variability looks quite different as well. So I started with an ice sheet example with the adaptive mesh refinement, so I'm gonna end on an ice sheet example. So we did some studies trying to better simulate the Greenland surface mass balance. And so this here is just a graph of how many grid cells makes up the Greenland island, which is the largest island on Earth. And so in the 1 degree and 2 degree models over here, which are in the blues and the greens, you know, it's a couple hundred grid cells making up the entire island. When you go to the Arctic 1/4 degree grid, you got about 2,000 grid cells, and then the 1/8 degree grid, 10,000 grid cells. And so if you look at the integrated precipitation over Greenland over time, the black line is your observations, and these coarser models produce too much precipitation over the Greenland ice sheet. And these variable resolution simulations here in the purple and the pink bring their precipitation rates down to more realistic values. And you see a similar pattern in the melt as well. And so your surface mass balance is more accurate at higher resolutions. And so why is this? This has a lot to do with the boundary conditions that I talked about. And so the depiction of the Greenland ice sheet in these 1 to 2 degree models are shown in these first 4 panels. They're quite pixelated. F19 looks pretty cool. This is actually the advantage of a lat-long grid because the convergence of the meridians towards the polar singularity gives you higher resolution at high latitude features. And then this is what the topography looks like in the 1/4 degree and the 1/8 degree models. So much more similar to observations. And the precipitation bias in these simulations is shown here, where green and blue is positive precipitation bias and red is a negative. And you can see that these coarser models tend to put a lot of precipitation in the interior of the ice sheet, too much. And as you go to the 1/4 degree and 1/8 degree, you start to alleviate those biases. And a lot of that has to do with, because in the 1 degree models, we smooth the topography so much that Greenland's like a pancake. And these storms that are coming in off the coast aren't aggressively lifted by the coastlines, and they penetrate further inland. Whereas at higher resolutions, Greenland is sufficiently steep, and so you get this aggressive orographic lifting right at the margins that wrings out the precipitation and prevents the moisture from intruding further inland. Yeah, so, and then the last thing I want to talk about is the melting aspect of it. So we did a idealized warming experiment for the workhorse 1 degree grid, which is FO9, that was the latitude-longitude grid, and then the Arctic grid. And we basically subjected them to 1% CO2 increases for a few hundred years. These were coupled with the ocean model, and they also have a dynamic ice sheet. And so we can do projections of sea level rise in these idealized experiments. And here is what the global mean sea level rise looks like. And the blue and the green are the 1 degree model, and the yellow is the Arctic model. And so it actually doesn't contribute as much to sea level rise. And that has a lot to do with there's actually a lot less melting that occurs when you warm the climate. And this actually has a similar geometric argument to the precipitation. So the equilibrium line altitude is the elevation where your net surface mass balance is 0. So for elevations lower than that, you're in the ablation zone, meaning you're net on an annual average, you're melting on net. And above that, you're in the accumulation zone. So in a warming world, the ELA rises and your ablation zones expand. But the amount of the expansion of the ablation zones for a given ELA rise is a greater area of the ablation zone is exposed. Whereas if you have a steeper Greenland ice sheet that's more accurate, if you raise the ELA, the amount of area of the ablation zone expansion is not as large. And so this plot here, going back here, is showing the ablation area is a function of ELA. And so as the ELA rises in the blue and the green, the 1 degree models, the ablation zone expands more than in the variable resolution, which has more realistic topography. And so your warming feedbacks are more accurate, and they suggest they're not as severe as if you were doing this with a 1 degree model. So that is all we have time for, and I'll take any questions you guys have.
Questions? Yeah.
I have a question. Is this also going to be able to be applied to the ocean side as well, to maybe MOM6?
Yeah, so right now it only applies for the atmosphere model and the land model. And if you're running a data ocean, then it applies to that as well. But MOM6 is latitude, longitude, or it's a tripolar grid, right? It's really hard to create refinement with that. I think the answer is no, but that regional MOM6 for higher resolution applications, I think it's something that we're beginning to support. So maybe in a limited area model, but not a full global model.
I was wondering if there has been any work or if there's the capability to add isotopic tracers to a variable resolution, like over a smaller area, like over the ocean.
Well, you'd want those tracers to be able to vect into the coarse region too,
Yeah.
right? So you'd have to have that active everywhere. And the answer is yes. I mean, there's folks who have done that. And so in theory, yes, and in older code bases, you can actually make it work. But isotopes are something that we are planning on having greater support for in the future so that more users can use it. And so the answer is yes, it's just, it's hard right now because you have to use an older code base or you have to wait until we put a more robust implementation of isotopes into the model. But variable resolution wouldn't be an impediment to doing that at all. It's just additional costs in the die core for adding tracers that need to be vectored around, and then the physics have to deal with the very hard physics of isotopes.
Okay, so it would be like pretty costly.
It's pretty costly.
Okay, okay, thank you.
Yeah, thanks Adam for your talk. The perception has always been that variable resolution CSM gives added value. Is that the case all the time, or do we expect that there are certain cases that it doesn't give added value?
I think some people run quarter degree and eighth degree variable resolution in the hopes that convective processes would be better resolved. And I think that expectation should be hampered and tempered back a bit. Because the resolution to even what they call permit convection is about 3 kilometers. Resolving convection is about 100 meters. And so I would say that if you really want to understand the diurnal cycle of convection and all these things, you need to go down to 3 kilometer resolution at least. And so you need to use a non-hydrostatic dicore. And so, yeah, I would just temper expectations of going from quarter to eighth degree and expecting that all your convective processes are well represented, because it's not, doesn't turn out to be the case.
Follow-up question on that. Even if, say with the regional alignment, let's say you could resolve maybe something like convection or something you're trying to do that can only be resolved on those smaller scales. If it's something that the model has a built-in parameterization for, like how do you make sure that you're not, and you're using that same parameterization everywhere like how do you make sure that that same parameterization is still valid in the coarser and the finer resolution regions, and you're not somehow double counting if you were previously parameterizing something that's now actually explicit?
It's a very, very hard problem. And there's really no uniform scale-aware convective parameterization that I'm aware of. There are attempts at it. And so I think the answer is whatever your solution is, it's not going to be perfect. One way that you can maybe hack it in is you could have something that's a function of the grid cell area that sort of turns off the convection when you're higher resolution and sort of leaves it intact at lower resolutions. I think that's a pretty imperfect solution, but it is something that would at least prevent you from having these resolved convection competing with parameterized convection in the high resolution region. But as I said, like even at 3 kilometers, you still need a convection scheme. Like the model can only do like these really deep plumes. And so shallow mid-level congestus needs to be parameterized even at those scales. And so that's where it gets really hard, because it's not clear that you can just turn off all the parameterizations.
Yeah, I wonder when you calculate the ELA elevation change from the now to future, like is this like, how did you calculate that slope or shape, and then is this like averaged over the Greenland area or?
Yeah, I mean, it's the way you would compute it is, so the Greenland ice sheet is this parabola, let's say, and the ELA is some contour along that parabola where the surface balance, net surface mass balance is 0. And so you would do a line integral over that contour for that elevation to get sort of like, okay, so you have that contour interval, so it's just this plane that goes into the ice sheet. And so since we compute the surface mass balance on the ice sheet, you just find that contour, and it's this, if you wanted to like quantify that shape of that plane, that would be an interesting algorithm. But yeah, it's just given by where the surface mass balance is 0.
Yeah, Adam, is there a follow-up on, is there a sort of a tutorial to develop your own mesh up until incorporated into the model run? That seems to be a gap in there, because when you ask around, they talk to Adam, so.
Yeah, we had some tools that, and that were set up for CSM 2.2 to generate your own mesh from the generation stage all the way to the run stage. Since we moved from the new supercomputer Cheyenne to Derecho, those tools don't really work, they weren't maintained. And so we didn't have a very good software plan for that. So the answer is, if you want to do it, you kind of have to take some of the tools that still work and then some workarounds that, yeah, like you'd have to contact me to find out. And, that's not idea, and I've expressed that, and so, in the near future, we will have a robust tool that any user can use to generate their own mesh and encrypt it to runtime. I'll say that MPass is a different workflow, and technically, so MPass standalone model in M-cubed has documents, and it'll tell you, it has these predefined grids that you just rotate over your region of interest and generate all the data sets. So, but there still would be parts of the workflow, I think, where you would have to reach out to a CSM expert. So nothing that's completely independent for a new user right now.
We can take one last question. The last one, sure.
Okay, oh, I can wait, yeah, go ahead.
I was just curious about the hexagon grid that you showed, which MPAS I think developed. I'm curious how when you're trying to perform calculations for budgets, especially where you want to perform gradients and all that stuff on the native grid instead of doing interpolation, is that a trivial task similar to how we use, for other curvilinear grids, or is that much more complicated?
I don't think the hexagons make that, well, I don't want to say that, because maybe I'll just outsource that to UX Array has built-in functions that can do things like derivatives in the X and the Y direction on unstructured grids.
Okay.
And so you could use tools like that to do that. For budgets, I think it's just an area integral, so it kind of, as long as you have the area of the hexagon to dot it with, I think you're fine. I don't think it's any more complex than if you had a quadrilateral element. But for gradients in a certain direction, I would imagine might be more difficult with a hexagon than a quadrilateral, but I don't know, but yeah.
Okay, great. Let's thank Adam again. If you have more questions, we may be able to catch Brian and Adam in the break. Let's now go into the break and come back at 9:45. right, our next lecture is going to be about Earth system prediction using CSM, and we'll hear it from Steve Yeager. Welcome, Steve.
Thanks. Hi, everyone. It's great to see a full auditorium here. It's always fun to give a lecture during the tutorial. I'm Steve Yeager. I've been at NCAR a long time now, since '98, and I've stayed here and gotten into the Earth system prediction business for the past 15 years or so. So I tried to make this lecture kind of hit the sweet spot of not too basic, not too in the weeds, but you be the judge, and I look forward to your feedback. So we're going to talk about climate prediction, and it builds on the foundation of probabilistic weather forecasting. So I thought it would just get things started by thinking about how we do weather forecasts with ensembles. So we start from some initial condition of the atmosphere that has uncertainty, right? And so that uncertainty induces this butterfly effect so that different simulations with slightly different initial conditions follow different trajectories, and that's what's represented by this cloud of blue lines here. So there's forecast uncertainty associated with that uncertainty in initial conditions. There's also forecast uncertainty associated with model uncertainty. Is the model representing the relevant processes correctly? And the idea here is that we want to predict some future state of the real world. And what we mean by that is we want to have a probability distribution from our ensemble that is smaller than the climatological, the dashed curve here, the climatological distribution, which would be sort of a basic no-cost prediction would be the climatological distribution. So we are hoping that our initial conditions give us that constrained PDF. And when we're doing a forecast, we associate the most likely outcome with the ensemble mean of this ensemble of forecasts that we produce. So that's our deterministic forecast, which may or may not align with what actually happens. But hopefully the cloud of probabilities encompasses what actually happens. And so this ensemble mean is referred to as either the deterministic forecast, or I'll use the term signal. It's the signal that's common across these ensemble members. So it represents some kind of propagation of initial condition memory signal through the system. And we're familiar with this type of cloud of uncertainty from these types of maps, hurricane forecasts that show quite small uncertainty close to the initialization point shown by the X here, but as you get further out into the forecast, that cloud of uncertainty expands and represents a range of possible futures for the forecast. So we're going to follow the same type of thinking, but now we're going to expand the time scale into climate time scales and think about sources of climate prediction or climate predictability. And when we're talking about climate predictability, we have this range of sources of signal that range from pure initial value signal to boundary value signal, right? As you get into the decadal and centennial timescales. And so that weather forecast example is down here. We get signal or initial condition memory just from initializing the atmospheric state, and that lasts a few days, maybe a couple weeks. But there's not a lot of inherent long timescale predictability coming from the atmospheric initial conditions. But we can get other sources of predictability that extend into longer timescales, like soil moisture in the initial conditions or sea ice states can give us sort of sub-seasonal into seasonal skill. We think about modes of variability like MJO and NAO that have inherent memory. There's inherent memory in stratospheric processes like the QBO and sudden stratospheric warmings. And then when we get into the seasonal timescale, of course, ENSO is the big player. ENSO is a coupled ocean-atmosphere phenomenon that has predictability extending beyond a year in some circumstances. When we get out into the annual to decadal timescale, we're talking about large-scale, low-frequency modes of climate variability, so Pacific decadal variability, Atlantic multi-decadal variability, global mean surface temperature, right? These are modes of variability that have long timescale memory associated with primarily oceanic processes, although they are coupled. And then on the longest timescales, we're talking about deep ocean memory and forcing, right? So we can get predictability just from knowing what forcing is going to be on these timescales. And so I just want to hammer that point home. I hope this isn't too simplistic, but the distinction between weather and climate prediction. So we can think of weather as a ball dropped in this pinball. There's a lot of randomness to it. But if we drop that ball many times, we build up the weather statistics for a particular region and say time of year. That's what we call the climate. And so the climate is this background probability distribution of the weather. And what we're trying to do in initialized climate prediction is leverage these sources of predictability that tilt the statistics of weather, right? So all these factors shown on the left here, emissions that change the radiative forcing of the Earth system, or internal variability cycles like ENSO or AMOC. These are drivers that tilt the statistics, and it's really that change in the statistics of weather that we're trying to predict, not actual future weather events. So I think this might already be a review since you're in the last day of the tutorial, but traditionally when we're doing long time scale climate prediction, we're thinking about climate projection simulations where we are taking a coupled climate model and forcing it with our best estimate of future forcings out through something like 2100 here. And we can run multiple ensembles, so many Earths at the same time, all subject to the same forcing. And that's what's shown in the gray background here. So this represents, I guess, 40 different simulations, that gray spread, and then the black line is the ensemble mean of those. So the black line represents, again, the forced signal, the variability that's common across those ensemble members, and then the ensemble spread giving you some quantification of the internal variability uncertainty. So in this context, the predicted signal depends solely on the forcing applied. And when we run these large ensembles, we then have a means to decompose the variability into forced versus internal. And clearly, for global mean surface temperature, the forced signal is a dominant contributor to our ability to predict the future. All right, so I want to talk a little bit about this sort of conceptual breakdown of forced variability and internal variability, both of which are contributing to the regional environmental change that we're hoping to be able to predict. And when we use projection, large ensembles that are quote unquote uninitialized, they've lost all initial condition memory, then what we can do with those types of experiments is we can, again, compute the ensemble mean signal, which gives us the response that's coming just from these different forcing agents that we consider external to the natural variability, even though solar cycles are natural, but the way that we apply them is kind of as an external forcing. And alternatively, the ensemble spread, or the noise across the ensemble, quantifies the internal variability that comes from the fact that each of those different members has different realizations of small-scale processes in the atmosphere and ocean, different phasings of ENSO, different phasings of ocean variability. So we sometimes call that irreducible uncertainty in our ability to predict climate out decades into the future. But the topic here is initialized prediction. And when we look at initialized prediction ensembles, then this breakdown changes because we are starting all of our members from the same or close to the same initial state. So the ensemble mean in a prediction ensemble gives you both the forced variability and change plus the predictable part of internal variability. So that's part of the signal, is this predictable variability that comes from these internal modes that have predictability, right? So we can get signal associated with ENSO and with AMOC in our ensemble mean, and then our spread across the members is unpredictable internal variability. So we're kind of breaking down the internal variability then into predictable and unpredictable components where, you know, the turbulence in the atmosphere and ocean is an example of variability that we can't predict beyond a certain time scale. And so how does this work? How do we construct these experiments? Well, we initialize climate model simulations from our best estimate of the historical Earth system state, and that's represented here with the black line. Observations in quotes because, you know, we're using some sort of data assimilation technique to combine all of the available observations with the model to come up with some reconstruction of past variability. That's in black. And then we're initializing the coupled model from that. Once we initialize the coupled model, it's free to do whatever it wants, and we run these ensemble simulations that we call hindcasts. And we force those hindcasts with observed external forcings. And then we repeat that many times to generate a collection of these hindcasts, or a set of hindcasts. Use those hindcasts to evaluate the model's skill at predicting past change. And in this schematic, you can see, well, this looks like a pretty skillful system. It's able to, you know, more or less predict this downward trend, this zero trend, and so forth. And if we have good hindcast skill, then when we do an actual forecast into the future, we have some confidence that our system is reliable, that the forecast that we're making is worth paying attention to. So how do we do that skill quantification? That we can look at things like deterministic skill. So again, deterministic meaning what does the ensemble mean look like compared to observation? So the ensemble mean here shown by the red dot, how does it compare to what actually happened, the black dot, right? So we can do things like anomaly correlation coefficients between red and black and come up with a skill score. Or we can do things like probabilistic skill. This is where we're taking into account the ensemble spread across our hindcasts and asking, did the observation fall within that spread, right? So something like a Breyer skill score. So I'm not going to talk about probabilistic skill, but just wanted to make that point. There's many flavors of skill quantification that you can look into. And I want to make the point that when the initialization is the key step here that helps us predict the internal variability, and that kind of adds value over traditional projection simulations. but we are using forcing. So we are also able to predict the forced variability signals as we do in projection simulations. So we have two kinds of climate prediction systems with CESM then. We've got uninitialized prediction systems where the skill comes from accurately simulating forced variability and change. And for these, we expect skill for long time scales and large spatial scales. And examples of this type of prediction system are the large ensembles that we've created with CESM1 and CESM2. CESM1 was a 40-member ensemble, CESM2, a 100-member ensemble. Both of these started at some point in the past, either 1850 or 1920, so they've lost kind of all initial condition memory by mid-century, and this future prediction is really just a function of the response to the forcing that we are estimating into the future. And then contrast that with the initialized prediction framework where the skill comes from accurately simulating both forced and internal variability components. And we expect improved skill for short time scales and small spatial scales. And we have a number of examples of that I'm gonna walk through next. So we've got a CESM2 subseasonal system, a CESM2 extended seasonal system, and then a CESM1 decadal prediction large ensemble. So let's start with subseasonal prediction skill. This is a paper that you can take a look at, led by Jager Richter, came out in 2022. This system is really focused on this time scale, right, from weeks into maybe a season. And here's the design of this prediction system. The ensembles are initialized weekly over this time span, 1999 to 2020, so a 22-year set of hindcasts that run out 45 days into the future, 10 members for each initialization. So that, if you do the math, that's roughly 1,600 simulation years that went into this experiment. So a non-trivial experiment to perform, not just to perform, but also, and I haven't put anything down on this slide, but to initialize this system. That's kind of a whole nother body of work to come up with the initial conditions for each of these hindcasts, because you need to initialize all the components of CESM, the ocean, the atmosphere, the sea ice, and the land. And here's an example of what kind of results come out of that system. So this is showing deterministic prediction skill, and we'll start on the right here for DJF 2-meter air temperature. And what you're seeing here is a map of the anomaly correlation coefficient between the ensemble mean of the hindcast and the observations for 2-meter surface air temperature over land. And you can see that in weeks 1 and 2, that skill is very high, right? Very red, giving you a very accurate reproduction of the observed variability, but by the time you get out to weeks 3 and 4, you can see that skill has significantly degraded, and there's only a handful of regions where you really have maybe actionable skill at that extended weather forecast. And you also see here that the skill for temperature is considerably higher than the skill for precipitation. So weeks 3, 4 precipitation skill is quite negligible. If we look at this in terms of an aggregate, regional aggregate skill, DJF global land, DJF North America land, as a function of the forecast lead time, so weeks 1, 2, all the way up to 5, 6. This plot shows how the CESM2 skill compares to other systems, in particular the European ECMWF, which is sort of the gold standard, is shown in gray. It's always the top line here, the best subseasonal system. But then here's NOAA's CFS V2, the black line, and then various flavors of CESM subseasonal systems. So it's certainly comparable to operational systems that are state of the art. When we think about seasonal prediction, the experiment design changes. So for a seasonal system that we call SMILE, we did quarterly initializations, 4 times per year. These run out 24 months into the future, and we use a 20-member ensemble, so the simulation cost is quite a bit higher. And we've shown that with this system, we can do a pretty good job of predicting ENSO out through 13 months into the future. If you compare the blue line here to the green line, green is sort of the state-of-the-art ECMWF. So the CESM blue system is quite comparable, not quite as good, but certainly on par with what other systems show. And then this plot just shows time series of what that looks like. If we initialize in November and try to predict DGF Niño 3-4, you can see that the skill is very high. That degrades as you go further in time. So here's a November initialization where you're trying to predict 13 months into the future. For some events, the skill is high, but for other ones, it's not. And so that's kind of interesting to dig into and try to understand why there's forecasts of opportunity in some years, but not others. And then finally, just the CESM decadal prediction large ensemble is probing these longer time scales from years to a decade into the future. Here, we only initialize once per year, but we run these a decade into the future with 40 ensemble members, and this is the most expensive system, 27,000 simulation years. And what we find in that system is that we have really high skill at predicting SST in the Atlantic in particular, even out to these decadal lead times. So years 5 to 9 into the future, we're able to do a good job of predicting, in particular, the subpolar North Atlantic, but also the tropical Atlantic. And a lot of that skill comes from the fact that we initialized. So it's not just coming from the forcing, it's coming from initial condition memory. All right, so I'm gonna skip these and just kind of talk about just some outstanding questions in the field. We're interested in how and where we can increase climate prediction skill. It's just a big, outstanding question. So how can we improve the initialization step? How can we improve the post-processing steps? Or just general model fidelity, for example, with model resolution or model physics that can improve the process representation that will allow us to better represent the propagation of predictable signals through the coupled system. And along those lines, you know, a big topic these days is the signal-to-noise paradox. So how can we get more signal and less noise in our prediction systems? And I put a few references there if you're interested in that topic. We want to know what are the coupled mechanisms at work in these ensemble prediction simulations to answer what explains skillful or unskillful predictions. What are the processes at work? This is a different framework from standard climate model simulations because you're initializing from the real world, the model is drifting underneath you, and you've got coupled processes happening with a drifting background climate. So better understanding those processes. What can we learn about predictability mechanisms from multi-model systems is a big question. And then finally, how can we enhance connections with potential end users? So with that, I'm going to end. If you're interested, get involved. You can get involved by joining the Earth System Prediction Working Group of CESM. You can analyze existing simulations. You can propose new experiments and use working group allocation to conduct experiments. And then you can share your work and find out what others are doing by joining our meetings. So thanks for your attention.
Questions? Yeah.
I was wondering, or I wanted to hear more about how you look at this skill with INSO, like looking at the hindcast versus the observations. Do you just look at the general Niño 3.4 like variance or metrics, or do you pay attention to the model simulating like specific events that are in the observational record?
I would say both, right? So the black line here on the right is observations. So we're looking both at that aggregate skill, the anomaly correlation quantifies how well we do overall, right? So correlation from 0.95 dropping down to 0.41 tells us something about that aggregate skill. But then you can look at particular events, right? You could look at this La Nina event that seems to be skillfully predicted even at a 19-month lead time, to this canonical 97, 98 El Nino, where the skill, is good up to, maybe 16-month lead time, and then we're really not able to predict it at any greater lead time. So I would say both, although trying to quantify skill for particular events is a little bit ambiguous in the sense of how do you quantify skill for a given event.
Because would you also look at like how many ensemble members simulated that event, or just?
Right, so yes, you would look at the ability of the ensemble to encompass that event. So for in this plot, the shading here represents the ensemble spread. So you see that some members did do better than the ensemble mean, and you might then analyze what was different about those members that allowed them to capture that event.
So what states do you analyze, like soil moisture or the snow? And which of these contribute to the departure from the internal variability?
Sorry, can you repeat your question?
So which states do you initialize when you have to initialize the model? Like snow or soil moisture or something in the atmosphere? And which of these actually more contribute to the internal variability difference, like departure?
That's a good question. I mean, we initialize every field in the land model that is needed for prognostic evolution of that model, which includes soil moisture and snow cover. So everything is initialized so that the model can run. Now, the quality of those initial conditions is a great question that we're struggling with because we don't have great observations of snow cover, soil moisture, like for all regions extending far back in time. And that's a big topic now with the SPAT effort. I don't know if that's been presented here, but land-atmosphere interactions and the role of soil moisture in governing subseasonal prediction skill is a hot topic of research. So I don't know offhand how much that contributes to internal variability on subseasonal timescales, but I think the answer is quite a bit.
And I'm very curious about S2S time scale because it can predictability some skills. So I'm wondering what's the current level, predictability level for now for the S2S. And with the help of AI tools, can push the boundary forward, maybe up to over 2 weeks, real time over 2 weeks.
I didn't hear the last part. It sounded like you're interested in the current level of subseasonal predictability. So I did show, that result from Yaga's paper. I would say, take a look at this paper for an overview of what our current subseasonal skill level is using CESM, which, as I pointed out on the left here, is comparable to, although slightly less than gold standard systems like ECMWF that use full sophisticated data assimilation in their initialization, which we don't use. So that might explain part of why our skill is somewhat lower. But I would say this result, this general lack of skill in weeks 3, 4 for precipitation is ubiquitous. I don't know of any system that can do much better than this.
Yeah, but for extreme events like drought or some heat wave, you think a machine learning tool can outperform physical-based models, or which one you think is better at predicting extreme conditions?
I don't know. That was a question about machine learning
Yeah.
prediction
Yeah,
systems.
which one will be better to predict the extreme events? You think?
That's an open question. I think that machine learning models might be able to do better, and they certainly might be able to do it with more ensemble members that can encompass extremes. Here we're limited by the cost of running ensemble members, where you don't have that problem with the machine learning-based system. But the advantage of this type of dynamical system is that you can really dig into the dynamics happening within, our physics-based models, and furthermore, you can do experiments, right, to advance understanding. So, to me, that's a clear advantage of using a CESM-based prediction system, is the ability to experiment.
Hi, I was wondering, the results that you've shown for the different models are DJF, and I was wondering if that's representative of what you see as far as the accuracy or closeness to observations of the model across different seasons?
That's a good question. I don't know offhand for subseasonal. My domain of expertise is really more annual or decadal prediction, where we don't really look at seasonal things, it's annual things. Yeah, I'm just going to speculate that DJF might be a more difficult season to predict, just because of the variability in that season is higher than in summertime. But I would have to check Yaka's paper.
Thank you.
In the interest of time, I couldn't take more questions, but you can find Steve probably after the lecture. He'll be here all day. Okay, let's thank Steve again. Let's now get into the lab intro section. Where are our speakers? Interesting.
They're all sitting outside.
Yeah, I'll just hold them.
Okay.
That's fine, thank you so much.
All right, come on in.
Oh, that one will stay.
Okay, we're now going to do a lab intro for today's challenge exercises. As you can see, we have experts from all of the domains here to give you a short introduction. Yes, as we mentioned before, this is the challenge exercise we're going to do. Yeah, and I want to introduce our helpers today. So from the atmosphere, we have Cecile. You've all seen Cecile before this week, and Sophia gave us a paleo talk yesterday. Then we have Gunter, the land ice. He's here, yes, Gunter. And then we have Dave Bailey on sea ice. Cool. And we have Kristen, biogeochemistry, Alper on ocean, Rebecca on atmospheric chemistry, Rebecca's right here, and then Eric on land as our engineer. Okay, let's get into each of these components from Cecile.
Yeah, that's what you are going to do. So far, you have run BKS. I don't need any mic.
Oh no, yeah, it's in mic.
Okay. Yeah, then so far you have been running what we call BKS, which is a fully coupled model. There was discussion on why we call this BKS. Nobody knows. But basically, in a BKS, you had all the components were were active, except the lantais in this case, but they're talking to each other through the coupler. In the F case that you are going to do, it's when you are running the atmosphere, but when you are running the atmosphere, you are also automatically running the land model, and it's what we call a F case. And it's really similar the way that you create the concept is different, but otherwise the command that you use to run an F case are very similar to running a beaker. We offer a few exercises here in the page. Then you can use historical SST forcing instead of using fixed forcing. You can change the run starting date. You can increase the orographic height over the western US here, or you can modify the SST temperature in the tropic. Also, you can change the triggering threshold for deep convection overland. Then you have a bunch of exercises you can pick, and you can even go from one group to the other. You don't have to do all the exercise of the atmosphere. You can pick one of them and do the other one. I don't know what's going on. It's like dancing.
Yes.
Yeah, thank you.
You're telling us to do.
I don't know what's oh, yeah. Sorry.
Next we have Paleo.
Okay, yeah, so you could also choose to do the paleo challenge exercise today. So for that exercise, we're going to run a mid-Holocene simulation, which was about 6,000 years ago. It's an interglacial period. And so we're going to modify the orbital parameters and plan for that. But also, an important step when we compare a mid-Holocene simulation with a pre-industrial control is that when you change eccentricity and precession, that actually changes the orbit of the Earth around the Sun. You can actually change the length of time it takes to traverse the orbit. So your length of January will change when you change the orbital parameters. And so we're gonna do a post-processing step called calendar adjustment to make sure we're comparing the same part of the orbit from pre-industrial to the mid-Holocene. And so that hopefully will make more sense in the challenge exercise. And then then you can also run a CESM simulation with water isotope tracers and plot the output.
Chemistry, okay. So with chemistry, we have you looking at three main cases. The first thing is to run a chemistry run out of the box with either CAM-CAM or WACM. So you choose whether you want to do the mid-top or the high-top model. And then once you run it out of the box with chemistry, we have you change a reaction rate to see how that changes the chemical output. And then finally, we have some changing of emissions, which is more complicated than it first seems. It's one line here, but there's a lot of things you have to do. And that's chemistry.
Okay. Land and I cheated. I'm sorry. I have 3 slides. But my name is Eric Kluzik, he, him, his, and I work on the land as a software engineer, which is awesome. This is some of the science of the land group, the land model. One of the things we're going to be talking about is the fact that there's different ways to parameterize vegetation. We have a prognostic versus a prescribed vegetation model. You're going to run both and see what the difference is. We're going to talk about I cases. Our letter that we have is I, and I will say, we kind of make fun of our lettering for concepts, but it is really short. It's really brief. I can just say I work on I concepts, so that's awesome, right? Okay, so you're going to do a control satellite phenology vegetation thing. And then as a test, you run biogeochemistry. Does anybody know the difference between, or can kind of think what the difference might be between those two? Satellite phenology is that a prognostic? It's a prescribed, yes. And then biogeochemistry is dynamic or prognostic. Excellent, okay. And then there's another test you run from the satellite phenology where you change an input parameter. And so our exercise is, so you run a control case. So do you recognize the comp set? Does ComSet make sense? ComSet and resolution at the end. Does anybody remember how the resolution works? The FO9 means what? 1 degree, yes. And the G17 means it's the ocean. And what's the GL4? That's
this.
Yes, you should know this. This is land ice, glacier. Okay. And then you run the experiment again, and with a different ComSet. And then at what resolution would you run it? Since that the first one's the control.
You think?
You'd run it the same. Now, I'm also going to note that the ice model is turned off, and so you really don't need that GL4 at the end. Okay. Compare results. Run a new experiment based on the SP changing the input parameter, and then compare results and see what's different about this in one. And then questions. I guess we're moving on though. And this is my shameless plug. Shameless plug for my computing survey. We want to hear about your comfort with HPC computing and that sort of thing, and your terrible experiences, or well, maybe I shouldn't say terrible. Your experiences, difficult, challenging experiences with HPC computing with CSM. So, and that's the last of my cheating.
That's Ocean. That's you.
Ocean.
Hi everyone. So in the Ocean practical, we'll be working with the GComSet, which is the combination of the PAP2 Ocean model, the main Ocean model with CSM, and CESM as the two active components. And then we'll have this base case where we will run a GComSet in a configuration, a 3-degree configuration with the normal year forcing. That is a data atmosphere and data runoff forcing that gets repeated every year. And then we'll make some modifications to this configuration. We'll first turn off a parameterization called overflow parameterization to determine how it impacts the simulation. And then we'll modify the wind stress using the source mod mechanism in CSM. And then we'll run another ComSet, this time including the ecosystem configuration. And then we'll compare the results of each of these different configurations. Yeah, that's pretty much the high-level summary.
Next. Yeah, so we'll also be running GComSets, just to throw another letter out there. So this is the sea ice ocean. It has a data atmosphere, much simpler than that whole CAM thing, honestly. But anyway, yeah, so it's a really nice thing. I can't remember, I think we're just using normal year forcing, but we also talk a little bit in the exercise about this interannually varying forcing too, which can go over the historical period and so forth. And so we're specifying the winds, the temperature, the humidity, and everything we're reading from the Japanese reanalysis or the old core forcing, I can't remember now. But in this exercise with the sea ice, what you're gonna do is adjust a very sensitive parameter, which is sort of the albedo per se, but we're actually adjusting a snow grain radius. And what you'll see in this, and this is a sort of a sneak preview here, these two slides, but basically this is a big hammer and it really changes the sea ice distribution very quickly. And so you're only gonna run about a year and you'll see that this has such a huge impact. And we're basically gonna plot sea ice concentration before and after, learn about polar projections and so on.
Good morning, everyone. So since we are doing the alphabet now, in this experiment for land ice, you're going to be running a TComSet. And in which, in this experiment, you're going to actually, like, as Eric mentioned, the land ice is not turned on in all the BComSet experiments that you've been running this week. And so in this one, you're going to be able to experience what the impact of the climate would have had on the ice sheet with your BComSet experiment. And what it does, it takes all the surface mass balance information within CSM and send it to the airship model, which is going to evolve within the CSM framework. And from this, you're going to do an analysis on what happens to sea level and how it's computed offline and in the end. You will also learn what it takes to run this TG concept. There's some special configuration within the B concept that needs to happen because you need to save the couple of history files. If you don't have those, you cannot do this experiment. And yeah, you'll see what happened then if you're interested in it. I'll be in the room. I'm going to have to step out a little bit at some point, but Kate will be there too if you're doing this. So that's the two people you can go to this experience. Thanks.
Yeah, okay, so for the biogeochemistry exercise, we're gonna not actually be running CESM, but instead we're gonna be setting up two different cases. And you're gonna compare just like the inputs for those cases and how those cases are set up. So the differences between them are basically how CO2 is handled in the atmosphere. So one, we have prognostic CO2 and diagnostic CO2. So prognostic CO2 is more emissions-driven runs, and you might have heard about these. They are the primary mode for CMIP7 models coming up. And then the opposite of that would be the diagnostic CO2, where the CO2 concentrations in the atmosphere are prescribed. These are different because basically with the prognostic CO2, the emission-driven scenario, this is more like a fully coupled carbon cycle. So you have CO2 emissions to the atmosphere, and then the land and ocean sinks can take up the CO2, and that determines the concentration in the atmosphere that's left. And that's in contrast to the diagnostic CO2, where it's just prescribed, and then the land and ocean can just take up that prescribed CO2 concentration. And so you just set up these runs, and then you'll look at the differences in inputs between the two runs, because they have different file inputs that will help you learn about the differences between these two kinds of runs. And then I also put up a GitHub repo that is from the CSM emission-driven run tutorial that me and other VGC working group co-chairs put on during the winter working group meetings. And this is just a very short tutorial, but there's some really interesting Jupyter notebooks in there where you can actually do some analysis on some existing emission-driven runs in there, as well as a shell script that sets a whole emission-driven run up for you that's CSM2. So yeah, come find me in the lab exercises in the library if you have any questions.
Okay, this is going to be a really fun lab, and I hope you enjoy it. Let's now go to the library. I believe we have signs put up where you can find your specific sections so the helpers can go in an easier way. Yeah, get started. CSM model porting for the specific version of CSM 2.1, 2.5, and we will hear it from Jim Edward, our CSM software engineer. Jim, it's all yours.
Hi, good afternoon. Can everyone hear me okay? I can't tell.
Go for it. Yeah, Jim, you should be good to go.
Okay, good. So you guys have learned a lot about CSM this week, and you've, I think, discovered the incredible portability or flexibility of the model. It can do experiments in all sorts of domains, from a single column land to very high resolution, fully coupled global climate model. It can also port to a number of different systems, from your basic laptop all the way up to the largest supercomputers in the world. And that's what I'm going to talk about here. Reasons you might need to port CESM. Different clusters, operating system versions, and compilers all require different configurations. You might need to port if you're using a new HPC system or workstation. The system that you have isn't already defined in the config machines file that we'll talk about soon. You're using a new compiler or MPI library. And the goals of porting are to get CSM to build and run on the system and ensure correctness and performance of the model. There are several options for porting CSM 2.1. There are some predefined machine definitions, like Homebrew for Mac or CentOS 7 Linux for Linux systems. You can do a local port for a single user by using a definition in a home.seam directory, or you can do a complete port for a shared HPC system and send that back to us to keep in sync with our model updates. Some prerequisites that are required. You need to have a Linux or a Mac operating system. You need to have a CMake, the GNU Make system, HDF5 libraries, NetCDF libraries. PNetCDF is optional, but if you have a parallel file system, it's highly recommended. You need to have C and Fortran compilers. We recommend the Intel compilers, which are now available to download free. GNU is also available free, as is NVHPC. I believe NAG has a price tag associated with it. But we recommend the Intel compilers as being the primary CSM compiler. You also need LAPACK and BLAS math libraries. These are often supplied with the compiler. For example, Intel has the MKL libraries, which do the same thing as LAPACK and BLAS. And then if you're going to use CSM3, you also need the Earth System Modeling Framework, or ESMF. That's required for CSM3. It's also required for some Wacom configurations in CSM2. Okay, in the home.seam directory, you can put these configuration files in that directory to port to your particular system. Several of these are XML format files. XML format has a lint system that helps you make sure that the format of the file is correct, which I think is very handy. It can help find syntax errors very quickly. And then I tried to kind of write a flow chart here of how you go about doing a port. So you start out by editing your config machines file for your system, and there'll be things in there like what compiler you're going to use, what MPI library. If you use modules on the system to load those, the modules implementation is there. What batch system you're going to use, where in the file system you're going to create output files. These are all things that you'll define in the config machines XML file. And then the config compiler's XML file, this has a hierarchical definition. So for a given compiler, there's kind of a default definition of flags that you're going to use for that compiler. If you need to make local modifications for your system, you can define the machine in there and specify, you know, a modification that's only going to apply to your machine. In CESM3, the config compiler's XML file has been replaced by a CMake a CMake file. And then config batch has information about the batch system that you're using, the queues that you're using in the batch system, the wall clock time, the minimum and maximum number of tasks that you can run on. So you edit these 3 files and then try a case. If the case works, then you can go on and copy these back into the config files and then run the system test. If the case doesn't work, you need to figure out why and go back and edit the files again and then try again. So this flow chart is just something you'll iterate on until you get it right. And it you know, it could take several tries. Things that you set in the config machines file, I kind of just told you that, but the path to the default case, the build and run directories, the path to the input data, the input data for CESM is downloaded as you need it. So if you build a case, it will only download the input data needed for that case. But if you have several users on a shared system, it's best to have one global input data that all of them can use instead of each one having a separate copy, because the input data repository is quite large, and if you have multiple copies on your system, you could easily fill up the file system with duplicates. So yeah, also in config machines, you can set the supported compilers and MPI libraries. You tell it what operating system you're using, the number of tasks per shared memory node. For Duratio, for example, that's 128. Different systems have different number of tasks. Node name regex is something that will define the system so that you don't have to type in the machine name each time you create a case. And then the type of batch system, PBS and Slurm are the most common. We also support LSF. And then there's a couple that have that no longer exist, I think. Environment modules are something that's quite common, and you can also set environment variables that you need in the config machines file. Things that you might set in config compilers are compiler flags that can be applied to all the files in the build, linker flags and external library links. And that, as I said, the file is hierarchical. So there's a general section for each compiler, and then that section can be overridden by subsequent sections with a combination of compiler, OS, machine. You can set different flags for debug on or off, different models. So the model would be like the components. You can have flags that only apply to CAM or only apply to the Pop Ocean model. And MPI Lib is the last one. Things that you might set in config batch are queue names and parameters, like wall clock time and minimum maximum job size. Deviations from standard queue systems definitions, directives, like the pound PBS part of a script that you'll see, arguments that are added to the command line. And again, this file is hierarchical, and general settings can be overridden in machine-specific settings. The config workflow file is a flat file that controls the flow of a job. It might include running the model and then doing a separate post-processing step. It might also do some kind of iterative run, feedback, and adjustments. And it also runs the short-term archiving step that moves files out of the case directory and into a separate archiver directory for prosperity. And then we can test all this once you've done a port using the scripts regression test Python script. And in CSM 215, it runs from the seam scripts test directory. It requires that you build and install the CPRNC facility, which is also under seam. And it uses Pylint if you have that installed. And then there's the CSM ultra-fast ensemble consistency test, which is used for CSM2 to verify that your port is valid by comparing, rather than doing a bit for bit exact test, we'll compare to an ensemble of about 300 members that was run on Duratio, and it'll do a pass or fail to determine whether your runs fit within the bounds of the ensemble. And you can upload, so we have this 300 member ensemble on Duratio. You can upload 3 runs to this website, and it will test your 3 runs against the ensemble, make sure it's within the bounds. If it's within the bounds, it's considered a pass. If it's outside the bounds, it's a fail, and you need to go back and figure out why. Resources for help with porting. The first one is the CGD forum. I highly recommend that's the first place you try to get help. If you find a problem with the model itself, you can open an issue in the CSM repository on GitHub, or in the SEAM repository on GitHub. And then we've done your tutorial on CSM 215, but that's several years old and was used for the CMIP 6 experiments. We're getting ready for the CMIP 7 experiments and developing CSM 3, which is significantly different than CSM 2. The MCT coupler has been replaced with ESMF-based CMIPS driver and mediator. The data models have been replaced with the more flexible CDEPS data models. Config compilers has been replaced with CMake modules. There's more interchangeable component options. The POP model is no longer a part of CSM. It's been replaced by MOM. It's much easier to introduce new grids. Offline land fraction and mapping files are no longer required. And so that reduces the number of grid files quite a bit. The machines directory has been split up into subdirectories. So instead of having one monolithic config machines file with every machine listed on it. There's a subdirectory for each machine with small machine-specific files in that subdirectory. And that makes it much easier to see what you're dealing with. And then CESM has been split into several repositories, and what remains in CESM is primarily the Python workflow code. The porting information is now in a repository called CCS config. CMIPs and CDEPs are in their own repositories, and the model share code is now in its own repository as well. And then CSM can run on your laptop. It's obviously you're not going to do high resolution global climate model experiments on your laptop, but you can do single column models. You could do some pretty interesting studies with it. And with containers, we can make it much easier to port to your laptop. And then one popular variant of container is the CSM lab, which includes the Jupyter Lab environment, the basic tutorial. And let's see. If you don't have a local cluster, we can also run on AWS and I think Azure. It's fully pre-configured with no porting necessary. Cloud costs, though, are considerably higher than HPC systems, which limits the use cases for cloud. Also, you can find, we've had problems with output data on the cloud becoming very expensive overnight. And let's see, any questions or comments? Here's my email address. Yeah, I'll take questions.
Thanks, Jim. Plenty of time for questions. Yes.
Hi, Jim. I was wondering, like, is there some kind of time indication, would you say, for like porting CESM to a different supercomputer, HPC system?
Is there some kind of
like a time indication? How long do you think it would take?
How long would it take? Generally, you can do it in a couple hours.
Okay, sweet. Thanks.
Mm-hmm. Okay, I can do it in a couple hours. It might take me.
I tried this many years ago, Jim. It took me a couple of days. But that when I was a first-year graduate. Yeah, it depends on your system too. I don't know. I used Slurm at the time. Yeah. Questions?
All right.
More questions? No? Yeah.
I hope you've enjoyed your time in Colorado. I really miss being there. Yeah, I'll leave now. Take care.
Thank you. Thanks, Jim. Cool. Yes, more time for break then. Yeah, let's go to the. Which time? What time do we come back? Is that 2? Yes. Friday. Oh my. Okay, great. So now I guess we have a half an hour break now. Yeah.